we have two speakers for today, John Kennerson and Honor Bilgan, and I will introduce John. John will introduce Honor later. But Dr. Kennerson is a retired cardiologist with nearly 4 decades of experience, including his role as a founding partner of Cardiovascular Associates, where he developed tertiary level cardiology programs and served as medical director of Virginia Beach General Hospital's cardiology division for over 20 years. A graduate of the University of Vermont College of Medicine, Dr. Kennerson's career spans clinical leadership, teaching, and global health initiatives. As the co-chair of the World Hypertension League's Expert Committee on Blood Pressure Measurement and Screening, he contributed to the global hypertension guidelines and faith-based health initiatives. Co-founder of Colleagues in Care, he has led healthcare and education projects in Haiti, focusing on maternal health, hypertension, and resource-limited settings. Dr. Kennerson has been recognized with multiple awards, including the Medical Society of Virginia's International Service Award and the University of Vermont's Alumni Service to Medicine and Community Award. So the work today, I'm going to play a 4-minute video for you guys, which is related to Colleagues in Care, which will give you some context of the type of work that John and Tom and his colleagues at Colleagues in Care are doing, and then I'll pass it on to John. Give me one moment to share with sound.
A lot of people come to Haiti and see all the difficulties that exist here. But Haiti has a lot of beauty, natural beauty. Its strongest asset is its people.
Once you get into Haiti, you are hit right in the face by the great inequality. And it's a different world. It's a world apart.
On regarde les communautés, on regarde les gens qui sont démunis. En tant que médecin haïtien, des fois on dit ça qu'il faut arrêter, mais c'est une question de sensibilité. Donc on ne peut pas balancer.
There are few trained healthcare providers. A lot of them were lost in the earthquake in 2010.
They have 3,000 physicians and the population of millions. But you see, like the Chinese people say, yin, yang. For every bad thing, there is also a good thing. The earthquake has put us in contact with some very good people, so it has created a number of opportunities.
Our specialties are cardiology and obstetrics and gynecology, so that's where we can lend our own expertise.
Most of the things that kill people have to do with those two fields.
Hypertension is a huge problem in Haiti for both men and women.
It's a matrix of loss. What can we do to break up that matrix? You look around and you say, where do we even start?
We are so fortunate in the United States to have every kind of device, every kind of diagnostic tool, every kind of medicine, every kind of specialist. Picking it up cookie cutter and taking it to Haiti doesn't work. That's not what Haiti is asking for.
Nous avons besoin de pile bagay. Il y a un bagay qui est plus important pour moi-même, c'est ta éducation.
So what we're trying to really do is to set up a system that isn't dependent upon one individual, and to build a bridge that is between our international colleagues and our colleagues in Haiti.
We needed some tool to do this. IBM is all about smart products, smart solutions. There is no reason that we can't use Smart Cloud that was built for companies to really save lives.
Together we form Colleagues in Care.
The beauty of a cloud technology is that it level sets everybody, the wealthy and the not wealthy, the underserved or the well-served.
So let's for the moment put politics aside. We're colleagues in the helping and healing profession of medicine. We're in a bond of mutual support.
We've developed a network of colleagues, both nationally, internationally, and in Haiti, where we get together to collaborate on development of programs, educational tools for the communities, and best practice protocols.
You take evidence-based medicine and you alter it for the reality of low resource, and it becomes best possible practice.
That will become their program to be shared with everyone.
This was a very useful tool for us to ask personal questions and a good way for us to have long-distance medical education.
With a smart cloud that gives us access to the medical literature and will extend it out in doing medical education, this will teach us and help us in providing better healthcare.
You have people that are passionate about relieving suffering, and those people are banding together and they're transforming this country, and as they're doing it, they're making models to transform other countries around the world.
That's great. So, John, do you want to talk a few words?
Yes, thank you. And thank you for the invitation today. We're thrilled to have this opportunity. I'd like to introduce my wife, Elizabeth Hansen. Liz is a recently retired OBGYN who's here somewhere. There she is. And we are the co-founders of Colleagues in Care. We started working in Haiti, used to say 2 decades ago. I guess it's pushing more like 25 years now. And we initially did things like water projects with some civil engineering marvel project. You know, some people think about just drilling a well. This was 2 miles through the mountains, and we were well on our way with multiple projects. And then January 12th, 2010, we had the catastrophic Haiti earthquake. Lisbeth was actually in country teaching that day and got pulled into action. And we had to reevaluate what we were doing. And that's when we formed Colleagues in Care to really focus on educating our colleagues and in solidarity with their needs. We were overwhelmed initially, like 60 groups wanted to join us. And so we retreated to our areas of expertise as a cardiologist and an OBGYN. Lisbeth continued to do her ultrasound training, ultimately becoming the head of the International Society of Ultrasound and OBGYN Global Outreach Program. I got involved in the World Hypertension League, and as noted, was involved writing some guidelines and statements on blood pressure measurement, and also was named an envoy for medical missions and faith-based organization outreach. And so with that in mind, I had an unexpected opportunity about a number of years ago where my clinical cardiology career was truncated due to a medical issue, and decided that that was an opportunity for me to start writing. And so that we did something that we've named the Cumulus Lift series, which is now a series of 6 parts, and it really has everything to do about hypertension in low resource areas. We are putting it out now, and we'll be doing that through a classic mechanism of printing, but also with AI. And we're really intrigued by what you guys have been doing with diabetes in the Indian Health Service. And let's put a bookmark there because that is something that we may want to come back and talk about, because it's an area of intense interest for us. Today, though, I want to talk about something that we have adopted as a principle of best possible practice. And by that, we mean that you have a marriage between evidence-based medicine and reality-based medicine. I found that I would sit in conferences, and people would talk about, having to mandate the use of automated devices, and I'd have to put my hand up and say, well, a lot of these places don't have electricity, and the batteries are really a problem. So I was very fortunate that we knew global health people and nursing people at Old Dominion University, and we got introduced to Owner. And we started talking about this challenge of having devices, that manual devices that you have to train everybody and keep them up to date. Automated devices, you need, a power grid that's reliable. And Owner came up with this brilliant idea. And Owner sort of is up here, and sometimes as a cardiologist, I have to sort of try to figure out what he's talking about. But he has a really good way of explaining things, which I think you're going to see. And so he explained this concept of using vibrational energy. And, to a sailor, he was able to say, it's kind of like a flag or an uncontrolled sail that's just flapping in the breeze. And then he started talking about a cantilever. And, we had done some building projects with decks, and I kind of knew what a cantilever was. And then he said, we're going to use piezoelectrics. So, of course, as Tom and I are nuclear cardiologists, scintillation and gamma cameras, that made perfect sense. So we did an initial study as a feasibility study, and it was promising. And I'm sure that Owner will talk about that. And I'm thrilled to see maybe some rekindling of interest, because I think this really has a lot of potential. We lost momentum a little bit. I got involved in other things. Owner went to Rutgers, and again, momentum was lost a little bit. But I think you're going to be very happy and intrigued by what he has to say. So let me go ahead and introduce him. Owner started in Virginia. He was at Virginia Tech, where he got both his master's and PhD in mechanical engineering. He's now a fellow of ASME, American Society of Mechanical Engineers, and he's an associate professor at Rutgers in the Mechanical and Aerospace Engineering Department. He also did some postdoc work in Swansea University in the UK. So without any further ado, let me introduce our good friend and colleague, Owner Bilgen.
Thank you very much, John. I really appreciate that, the kind words. Koyar, thank you for the opportunity to be here, and to the rest of the colleagues here, thank you for attending and being here. So I was, as John mentioned, in 2014, I met my colleague Müge Akpınar-Elçi at Old Dominion University, and we were talking about some ideas, and eventually I connected with, through Müge, I connected with John, and then later to Elizabeth. So that's the period where we started this work. I'm in mechanical and aerospace engineering. I work with various dynamic systems. Some of them include energy harvesting systems, vibration energy harvesting systems, or variable energy harvesting systems. So these are basically systems that collect a small amount of energy from the movement of the body, or movement of fluids or structures, and then convert that to electricity, and then save it into some storage like battery, to do various things, low power things. And this has been an active research interest since I would say mid 2010s, even earlier, and there's still a research going on. So through this connection with John and his work in Haiti, and the importance of blood pressure monitoring, we had some discussions and then came up with this idea. So I'll go ahead and start my presentation. Share screen. Okay, I think you can see my screen, right? Yeah. So this presentation is adapted from our one of the conference papers we wrote, we collaborated with John and Muge and one of my students, Rebecca. This was in addition to a journal paper that we put together with John and the same group on the Journal of Clinical Hypertension. And at the end of the presentation, I'll have those references listed. So let's just get started. So of course, I don't want to, I'm not the expert in this area, but this is knowledge that I learned from John. So we know that hypertension is a global health problem. We are aware that 80% of the healthcare costs are in low and middle income countries. In these places, there are very complex healthcare management requirements. And then there are significant resource challenges in the developing world. So one of the resources is availability of batteries. So the question that we posed for ourselves is that can we harvest some energy to power a semi-automatic blood pressure monitoring system or just any kind of a blood pressure and monitoring system? So the ideas that we had was that we collect some energy from the environment or the user. And then previously, this has been done through solar charge devices. Of course, these solar collectors or solar charging stations are now common. So there's one example. There was an Omron HEM solar, has a long charging period. And then another one can be a mobile phone augmented blood pressure monitoring system. Of course, the phone itself has to be charged. And then our proposal was to either use flow energy or vibrations to charge a battery, a rechargeable battery in the blood pressure monitoring system, or simply provide the power on demand during the operation of the system without charging a battery. And so actually, let me give one example. So one way of doing that would be something similar to a hand crank radio. You're probably familiar with this. You have a crank, you can rotate it to produce some power, and maybe wind the spring, and then that energy is stored in the spring by your rotation can provide some power enough to operate a radio or any other device for some finite amount of time. So we wanted to make this device as low cost as possible. So something like a hand crank radio, although you can find it easily, it still has a lot of moving parts that has to be assembled. So it is actually a quite costly device if it's added to an existing blood pressure monitoring system. So we wanted to make this as low cost and as simple as possible. To do that, we wanted to remove moving parts or number of parts as much as possible. So the question is that we have a semi-automatic device where most of the work is being done by the user. That's the pumping action of the cuff. So can we put something between the bulb and the cuff where the air is flowing to save some energy, to harvest some energy from that fluid motion? And as John explained, this could be something like a flag that is being flapped around because of wind, and then that flapping is motion, and that some of that motion can be converted to energy by some transduction mechanism. So the one part is of such system is the conventional electronics, such as the pressure sensor, the processor, a display, and maybe a wireless transmitter to a mobile phone. That's already part of a semi-automatic device. The part that we need to come up with is this flow energy conversion method or device. So we need to insert something into the flow and then maybe transform, like pass it through a transformer, a rectifier, conditioner, power management system, and maybe a capacitor or a battery. Okay, so the rest of the presentation is organized as follows. So we'll just look at that concept that we proposed. I'll show some preliminary analysis, then look at the work that we have done on commercial blood pressure monitors. We looked at power consumption of such monitors, and then we also looked at we also developed a prototype and I conducted some preliminary experiments. Okay, so our concept is as follows. So we're going to insert between the bulb and the cuff, we're going to insert something that's going to flap around or vibrate within that little flow, within the tube. These are, of course, for illustrative purposes. And then, so this is what that device looks like. So we have, imagine that this is a tube or section of the tube. Airflow is coming. It's going to go over this beam. That beam, you can imagine it as a flag. Flow over that beam or that flag is going to make this beam vibrate in up and down direction, and then or bend in the up and down direction. It might be fixed back here, and then that up and down motion will cause a strain or change in shape on a transduction element, such as a piezoelectric element. This piezoelectric element, when it changes its shape, it will convert the motion into electricity. And we're going to take that electricity, put it into a transformer, rectifier, conditioner, etc., some power management system to be able to store it. So as this flow passes by this channel or an orifice, and as this beam vibrates, more and more energy with every pumping action or inflation action, more and more energy is being stored into a battery, and then that battery will be then used to operate the semi-automatic portion of the blood pressure monitor, which is pressure sensing and basically slowly bleeding the air out of the cuff to continue doing the pressure sensing, and then of course some basic calculations, and then displaying that sensed pressure on the display or wirelessly transmitting it to a phone. So this is a very basic concept. I guess at this point I can stop and see if there's any questions about this.
So the mechanism, from what I see, is that the flow will move the cantilever, and that activates the piezoelectric transducer to create power.
Yes, that's great.
Yeah.
And to make that, yes.
Oh, sorry. No, go ahead.
No, I'm listening.
Just a general question. And you're probably going to get to it. Do you have to do so many blood pressures per day to appropriately power it, or is it just as you're doing one, you've got enough for the next one?
Yeah.
Realize it's a very simple question, but that's my level.
Yeah, that's correct. So the design problem here is to make sure that the number of inflation actions or bulb actions that you need to inflate the cuff for one measurement will also store enough energy to make that measurement. So the design,
Fascinating.
yeah, so the design, and that's possible. That's just a design problem. It's to put enough material here, conversion material here, and make this thing flap enough such that you can save or harvest energy more than you would need for one measurement. So it would basically be self-sustaining. You would not have to inflate more than you would just to inflate the cuff.
Thank you.
Yeah, yeah, good, very good question. Okay, any other questions about this idea? Okay, so let's move on. So the how do we harvest energy, or how do we convert mechanical energy to electrical one? We use a piezoelectric material. So piezoelectric means, piezo means pressure, so it's pressure electric. You apply pressure, it produces electricity. The reverse is also true. If you apply electricity, it produces pressure. These materials are very frequently used, so they're in your phones for many decades, actually. They're in microphones, they're in speakers. So anytime where you have an electric to acoustic interaction, piezoelectrics are used because you apply electricity, it creates pressure, the pressure then moves air and then produces sound, and vice versa. They can be used as microphones. They're used as motion sensors, accelerometers, etc. So they're very frequently used. They're all around everywhere in many modern devices. So what we want to do is we want to create like some sort of an orifice in this flow. So that orifice basically will speed up the flow, and then that fast flow will interact with this flag or beam. That beam will flap around in the up and down direction. And then on that beam will stretch and bend, and we will have some amount of piezoelectric material on it. And then that bending will cause the piezoelectric itself to stretch. And then that stretching will generate electricity. Okay, so we've done some preliminary analysis. So we've just looked at the very basic element, which is the piezoelectric material on some sort of a solid material, solid substrate. And we have models for this, so we understand how it works. As I said, we've developed a model previously that this was part of my prior research. So we can predict basically how much power is being produced for different parameters of such systems. So for an important parameter is how much piezoelectric material is on top of a non-piezoelectric material. So the thickness of this material compared to this material is a very key parameter. You can see that large amount of power can be generated at some thickness ratios. That's basically the ratio of this thickness to this thickness. If you don't get that thickness ratio correctly, it can produce low power. So various things can be achieved. It can work well if you design it properly, or it doesn't work at all if you don't design it carefully. And we know how to design it because of this modeling. We also have done some experiments to compare to our models. So we have a device here that basically shakes the base of a beam. It's right here, this orange thing. It's like a cantilevered beam. We shake the base of it. It basically bends under that base excitation. And then when it bends, it produces electricity. And then we looked at the power output as a function of, again, thickness ratio. That's the thickness of the piezoelectric to a substrate. We also looked at different types of materials, substrates, so aluminum, brass, steel. So that also have an effect. We looked at effective frequencies. where this vibration occurs. So the vibration does occur at a particular type of frequency of excitation. So this gave us, again, this is prior research, this gave us confidence in our understanding of how these things work. So we've taken some, we've made some basic assumptions and did some analysis of this new system that we are proposing. So we used the Bernoulli's equation to understand how the airflow speed connects, or how it relates to the pressure in this gap. So we've used Bernoulli's equation to develop some models. The idea here is that as this beam moves up and down, the gap, the gap here, the top gap for the airflow, and then the bottom gap for the airflow changes. When the gap changes, the flow speed changes, and the flow speed changes, pressure changes. So it's this, the opening and closing of the top gap and the bottom gap is what causes things to oscillate up and down. So we have a steady flow, continuous flow, non-oscillating flow, creating an oscillating movement. Okay. We've compared different gaps. The gap itself ends up being an important parameter of how this system operates. We looked at different gaps, and we saw that certain gap sizes create strong oscillations, certain gap sizes don't create strong oscillations. Again, indicating that if you design this properly, you can get oscillations and power output, and then if you don't design it properly, you don't get much. So next step is to understand the power consumption of commercial blood pressure monitors, because we do not need to reinvent the wheel. We basically want to use a semi-automatic device because it works well. We just want to remove the batteries and then replace it with this energy harvesting addition. So we looked at a fully automatic device just to understand how much power it takes if we were to do this entirely automatically. But our intention is to do a semi-automatic one, which means that the inflation action is actually done by the user, and we're going to take some energy out of that inflation action to power the rest of the electronics. So we looked at an Omron semi-automatic device and an A&D medical semi-automatic device. We looked at the power consumption during a single operation. So of course, the fully automatic one does the inflation action itself, which is a large power consumption. So the nominal power consumption, sorry, the average power consumption for one measurement was about 1.23 watts. Small amount, which is good, because from the flow, we're going to actually produce a very small amount of power. But a semi-automatic Omron device actually has 40 milliwatts, which you can see like very, very small compared to a fully automatic one. And then A&D medical semi-automatic device had even smaller power consumption for a single blood pressure measurement. It was 8 milliwatts. So these are small numbers, although the energy in the flow is also small. So we have to create a device and a flow energy device that can produce such amount of power. Okay, so we developed a basic laboratory type or a bench type prototype. So the idea was that we take this concept here and then turn it into some sort of a prototype, not for implementation, but for experimental purposes. So we have some interesting parameters here, like the gap size and the length of this beam and how much this beam is inserted into the gap. Those are very critical parameters that will change the power generation significantly. So we wanted to create an experimental setup such that we can change these parameters and then see what their effects are and then compare it to our predictions. So we developed this apparatus. So it kind of looks like a chamber, a wind tunnel, or a pipe, a duct. So the flow comes in. This is basically an idealized prototype. The flow comes in, it goes around this beam that will flap around. It goes into the two gaps, top gap and the bottom gap. And then inside of that gap, there's a beam, which will have the piezoelectric on it. And then that beam is fixed at the back. So the beam is pointing towards the flow. And then as the air passes through, this beam will vibrate. Now, this allows us to insert the beam more or less into the flow or into the gap. That changes its actually stiffness compared to the forces applied by the gap. Another adjustment that we have is that this orifice or the gaps can be adjustable. So this piece is on an incline. So if I bring this piece backwards, the top gap will open. If I take this piece and I bring it backwards, the bottom gap will open. So I can also, with the use of this prototype, I can also control the gap size. Again, the gap size and the beam length or the beam insertion are critical parameters to either produce more power or less power. So we used 3D printing to fabricate this prototype. Of course, we wanted to make it quite large, such that we can manufacture it easily, and then we can use supplies in the laboratory, and we can change its parameters by hand. So typically we scale things up or scale things down depending on what the real system is. In this case, we scaled it up such that we can manufacture it easily and cost effectively. So here's the bulb for reference. Here's some wires. Here's that base of the beam, this black part here, the black line is the beam itself. You will not see it, but the piezoelectric beam, piezoelectric material is also on it because it's very thin. It's hard to see. And then here are those adjustment pieces on an incline, and they can be moved up and down. So we had the help of summer camp interns. We had about 5 of them, so I've set things up for them, and then they've conducted the experiments. We've checked the experiments later on. So here are the most interesting or important results of the experiment. So here's the voltage output. The parameters that we tested were the gap to base distance. It's this distance here. So the distance from here to here. So how much of the beam is being inserted into the gap? That's this distance here. And then we looked at the gap itself. So we tried a 1.8 millimeter gap. That's the gap here. And we tried a 1.6 millimeter gap. So we tried 2 gap amounts, gap sizes. We tried multiple distances, insertion distances. And as we were anticipating, really interesting things do happen. So when the beam is inserted very far into this gap here, not much voltage is being generated. However, after a certain amount, so for example, about 2 inches or 2.5 inches distance between here and here, a significant increase in voltage can be seen. Another interesting thing is that, you have a very small change in the gap. We go from 1.6 millimeter gap to 1.8 millimeter gap. It's this distance, this very small distance here. So you go from 1.6 to 1.8, all of a sudden you see a very large and consistent increase in voltage. So the why? Because this is this flow phenomena, flow over this beam, the gaps opening and closing. It's a nonlinear phenomena. So small effects or small changes create large changes in the outcome, and that's a very common and well-known thing. And then we always utilize such nonlinear phenomena. So again, this simple experiment shows that careful design, clever design can really make a big change in the amount of voltage being produced and amount of power being produced. So that basically concludes the presentation. So we were able to, come up with some sort of a prototype, shows that there's feasibility. We've made some calculations on how long it would take to charge under these conditions. A lot of future work exists, of course, so we need to do detailed analysis of this transient and steady state response. We need to analyze charging and discharging characteristics using this energy system. And of course, we need to do design optimization. Those parameters that we played with, we need to come up with an accurate, very accurate model. Using that accurate model, we do computer simulations. Many of them do design optimization such that we can pick exactly the correct parameters. And then using that model and using that design optimization, we scale this device down, such that we scale it down. It needs to be large enough to produce enough power to sustain a single measurement by the number of inflations that are necessary to inflate the cuff. So that's my presentation. Here are some of our papers. There's a paper, conference paper, and then one journal paper on Journal of Clinical Hypertension, and another one at a different conference. So thank you for your attention. I hope I didn't.
Thank you very much, Onur, for the presentation. So now we are open for questions. I will start here and we follow up with others. So this is actually very interesting. So one maybe more technical question. I remember on one slide you had that for every measurement with the A&D blood pressure measurement system, you had about 8 milliwatt that was needed for a single measurement. And I know this might be a research in progress, but I'm just thinking, with every time that you inflate the bladder, how much power can you create? How many milliwatts?
With every inflation?
Yes. How many times you need to inflate this to do one measurement? And you were just talking about the fact that you want to have a quantification of this. It's just how long does it take to charge this for a single measurement?
So that's the part we don't know yet.
Okay.
So but the answer is that you can design it to be anything. I mean, we can put enough materials, piezoelectric material, or large enough piezoelectric material, or any other type of conversion mechanism to do it with once. Or we can do it for 30 times or n number of times. It's the design optimization. The step that is needed is design optimization, which says that how much material are you willing to put, which is cost, right?
Oh, is it only cost or also the size of the device as well? That doesn't affect the size, all right?
No, size. So size then relates to the cost, right? So that's correct. How much size are you willing to make, and then how much materials are you willing to use? But again, our initial estimation. So, for example, from our preliminary experience, 20, 30 seconds of this inflation action was more than sufficient, right? Without any optimization, which indicates that we can easily design that. Not necessarily, of course, this would not be done inside of the tube itself. It would be done inside of the semi-automatic box. So we would include a small energy harvesting chamber, and then that chamber would be perfectly reasonably sized, and then it would have a reasonable cost. But again, the important thing is that only design optimization can tell us but for a target cost and a target size, that this is the amount of inflation that you need.
That's very interesting. Anyone else having questions here in the audience?
Yeah, maybe a couple of comments as much as questions. So the World Health Organization had really pushed semi-automated devices. They're accurate, they're accessible, and the big thing was cost. But recall the difference between a fully automated and a semi-automated device. A fully automated device, it measures the oscillometric measurement at the arterial level, and then with some sophisticated algorithms, we'll decide, what's the systolic and what is the diastolic pressure. Now, with the semi-automatic, and that has a rigid cuff, and so the rigid cuff is then expanded automatically by the as owner showed, much higher power requirements. Now, with a semi-automated, it's not a rigid cuff, it's a soft cuff. So that tends to be, if you think about the old-fashioned way of taking a blood pressure with a soft cuff and using the auscultation, that you still have to blow that cuff up so that it's occluding the artery. So how many compressions it takes might be somewhat of a variable. And so that's a little bit of a difference in the semi-automated device. One of the things that I found intriguing is that if you think about redundancy or what can go wrong, if there was still enough power to light the LED display, if there were issues, you could still use that semi-automated device and take a manual measurement by listening and by manual technique, because you'll be seeing, when you're hearing, you'll be seeing the numbers as the pressure comes down, even though the oscillometric automated device may have failed or maybe didn't have enough power. So I think that is, there is a critical difference in the gradient from manual devices, with auscultatory, listening versus the semi-automated and the automated. And this is one reason initially the WHO had pushed for the semi-automated devices. But just as background.
Yeah, that's great. So there is a plan B just in case.
Yeah, some great comments, John. Owner, it's Tom Rocco. As as someone who aspired to double electrical engineering early on in his undergraduate career, and then quickly realized it'd be a lot easier to go into medicine. Just again, a couple of simplistic questions. First of all, elegant design and a great presentation. Thanks so much. But just a quick question. If you had to crystal ball, and obviously there's going to be a trade-off. It's cost and size and size of the device and generation of the needed energy. But if you had a crystal ball as to a semi-ideal cost to device size and energy generation ratio, what would you expect the size of this device to be?
So from the other prototypes and other systems that we've looked at, I would not imagine anything more than an inch size, several inches.
That's amazing. Yeah,
so
that's what I thought you were going to say. Yeah, okay. That's amazing.
It's a chamber, right? So
See,
within a few inches. So it's not going to add, and it could be, I think, integrated into the existing into the existing machine of the semi-automatic device.
Right, that's what I was getting to. It's not going to need to be an add-on device. I mean, if this works out the way it should, and my gosh, I think it should. I mean, this would be integrated into the device. Yeah.
It would be integrated. I think it would still have, it probably would still have a battery compartment, in case a battery, if the battery, you can use the battery, but it would be like multi-mode, right? So if you want to use the battery, you can use the battery. If you run out of battery, it will still operate
Sure.
for one measurement. The important thing, another important thing is that, again, the simple example would be a hand crank device or a hand crank radio, something that you wind up, and then that would produce energy. That would be much larger in size, and then it has a lot of moving parts.
Sure.
So you can never make a device that's kind of a traditional conversion device as small and as cheap as possible, as you would be able to do it with this idea.
Vibration. Thank you so much.
Well, thank you, Tom.
We're getting close. We have 1 more minute. Maybe I just use this. Normally, this is a question we ask everybody who gives a talk here. How can we help? Is there any way we can collaborate or bring something to the table?
Okay, so thank you. So we, as John mentioned, right? So we did look for some funding opportunities in the past. And I've been doing other projects, so our attention kind of moved away from this. So we need to basically put another, master's or PhD level student on this project to then produce a working prototype, or first prototype that can be implemented. So we need to take the existing modeling, improve the modeling, do design optimization, find out what these critical parameters are, make a prototype, a variable, actually implementable prototype, and then show that it works, at least show feasibility, and then we will make additional simulations and modeling and design optimization to make a second prototype that then we can do like some beta testing. And then it would then be, of course, moved into some sort of a commercialization if there's an interest in that.
Yeah, at that stage, that's somewhere that maybe we can talk separately if it gets to a point that you have a prototype. And we talked about it, possibilities that maybe we can help you with some SPIR, a CTR grant. And I told you blood pressure measurement has been always an interest of mine as well. So maybe we keep the channel open and see where you go with things and engage whenever you find it appropriate.
Yes. I think the initial stage is to find some funding opportunity for a master, more ideally a PhD level graduate student, and then they would they need to do this modeling and design optimization and additional lab experiments, such that we can have a fully functioning, a full prototype.
Yes.
Just a quick thought. Owner, I'm sure you've got plenty of candidates at Rutgers, but Kuyar, could this be something to be farmed out to maybe UND or
actually, one of our faculty members works on non-invasive blood pressure measurements. I invited him, and he had to leave a bit earlier today, but that's why I made sure that he would be here, and I'll talk to him later. I mean, definitely there is interest, but maybe we should have a separate meeting about there are some logistical considerations when there are two universities involved
Sure.
in research in terms of
Sure.
IP and everything. Otherwise, I mean, I'll be very happy to have my colleagues and I to just get involved and see where we can bring a student in. It's just that maybe let's, Honor, you have my contact to my calendar. Put something on my calendar whenever you are ready, and let's talk about it. There are some resources maybe we can pull in from North Dakota.
Okay, thank you.
Okay, we are actually 2 minutes after our. Thank you very much, Honor, John, Tom, and Elizabeth for being here. Great talk, and you guys are doing a great job. We will see how we can. There's a lot of synergy, as you can see, with what you do and C2 Ship, and let's see how we can collaborate. We'll be in touch.
Thank you very much. Thanks to everybody for attending.
Yeah, thank you all.